Welcome to the solutions for the third homework assignment on volumes by revolution. This was the first problem assigned, page 392, number 21. We have three equations that describe the border of the area we will rotate. Y equals x, y equals 1, and x equals 0. And then in the previous paragraph, the x-axis is described as the axis of revolution. In the top right corner, there are a couple of questions. We need to answer the question dy or dx, and we need to answer the question circle disk or washer in order to pick the right strategy. The answer to both of those is going to come by looking at the x-axis, which is the axis of revolution. The very first thing we're going to select is the dx problem. The reason is that the x-axis is a horizontal line. Any horizontal line for the axis of revolution makes it a dx problem. The second thing we'll select is washer. This is a dx problem with washers. The reason it's a washer is because y equals 0, which is just another way of saying x-axis, is not a border. If, hypothetically, y equals 1, which is a border, was also the axis of revolution, that would represent circle disk. Anytime your border equation and your axis of revolution are the same, that's a circular disk. In this case, our axis is y equals 0. Y equals 0 is none of our borders, so washer. Dx problem because it's horizontal. Washer problem because the axis isn't a border. We'll do slice, approximate, integrate in just a moment, but do want to do a basic sketch. We have our line y equals x. We have our horizontal line y equals 1, which I'm going to move up just a little bit so that the area is clear. And then the other item is the x-axis itself. The line x equals 0 itself forms one of the borders. The area that we'll be rotating is the area kind of inside this triangle. Now that we've graphed it, it should be pretty clear why it's a washer problem. We're going to have a small radius. That small radius travels from our axis of revolution to the lower boundary of the function. Sorry, p-type. And our bigger radius travels from the axis of revolution all the way to the top boundary of our function. So those are our two axes of revolution. When the area is rotated, you get a big washer, or you get a big circle from that large radius, but you also get a smaller circle from that small radius, and that forms our washer. So step 1, slice. We just want to identify the geometric shape for each vertical slice. We've already identified that it's a washer because of the border, so we just need to say its area as a basic geometric equation. It's actually a two-variable equation. It's one of the only two-variable equations we use. Pi, big R squared minus little r squared is our standard representation. You can write that area a couple of different ways. I'd like us to use this specific structure because it makes the antiderivatives a little bit easier. The heart of every problem is the approximate step. Our goal is to produce an area equation again, but using x as our variable instead of big R and little r. In order to rewrite big A, we must first rewrite big R and rewrite little r. if we look at the picture, it should be pretty clear because our outer border for the area, and when I say outer, I'm referring to the border farthest away from the axis of revolution. That outer border is the constant function y equals 1. So our big radius is constantly the value 1. But we need an approach that's always going to work, especially if the visual is hard to create. So our approach, outer function minus axis. That's foolproof. That always works. In this case, our outer function is the constant y equal 1. Our axis of revolution is the constant y equals 0. So the function 1 minus the function 0 is our outer function minus axis. We get 1. R of x is the constant 1. Little r should be pretty clear from the picture because y equals x changes. The farther along you are, the bigger a little radius. Or the closer to x equals 0, the smaller the radius. So it does vary. The process for identifying little r of x is very similar. It's inner function minus axis. When we say inner function, we're referring to the border that is closest to the axis of revolution. So this horizontal line is close to our axis, so it's inner. I'm sorry, this linear equation is close to our axis, so it's inner. This horizontal equation is farther from the axis, so it gets that label of outer. So inner function, y equals x, so x. Axis, y equals 0, so 0. And then what we get is just the function x dictates the size of our inner radius at every value of x. We can now rewrite our area function. Out goes big R, and in goes 1, the constant function 1. Out goes little r, and in goes the function x. So that's our big R squared minus little r squared. And we can simplify that just a touch. 1 minus x squared. We're almost done with our setup. We've done slice. We've done approximate. So now we just need to identify the integral, or the integrate step. The volume of a solid is always equal to the interval from a to b of a of x dx. In this specific case, our a value starts at 0, and hopefully we can see from our picture that b equals 1 is where the line y equals x and y equals 1 intersect, so that intersection sets our b value. And our area function we've identified as pi 1 minus x squared dx. For the homework assignment, I did not require you to work things out by hand using antiderivatives. It was okay to use a calculator. On the next screen, I'm going to work this out by hand just so we can practice understanding how to use antiderivatives. Because eventually we want to be able to do this entire process by hand with no technological assistance. So we have our integral, the volume, equal to the integral from 0 to 1 pi 1 minus x squared dx. I've highlighted pi because it's a constant. And I've gone ahead and added this circular dot to represent a constant times a function. That allows us to use the constant multiple rule, or the ability to factor out pi. The reason that's a nice step is it makes the antiderivative a lot easier. Now we can just focus on the antiderivative of 1 minus the antiderivative of x squared, which is x minus x cubed over 3. And we still have 0 to 1 as our limits of integration. This is our g function. We're going to find g of b minus g of a, and we'll just save multiplying by pi for the last step, because we've pulled it out and saved it for later. G of b is 1 minus 1 cubed over 3, and g of a is 0 minus 0 cubed over 3, which clearly equates to 0. Almost home free, we have pi 1 minus 1/3, and 1 minus 1/3 is 2/3, so 2/3 pi is our volume. Smiley face. All right, click the next video if you would like to see the next homework problem worked out, number 22 for page 390.